Okay, beautiful. Okay, so continuing on with integration, hopefully you have a pretty firm grasp of the basic idea of taking integration. We're going to take a break from that and talk about the physical representation of an integral. Okay, so that is area, by the way. That's because it says area right there. And we're going to understand the concept of area. I know you understand the concept of area because some of you had a fantastic geometry teacher. However, we're going to talk about the concept of area as it relates to calculus and integrals. We're going to find the area of some rectangles. Done. We're going to talk about limits. How can we reduce the work of finding the area of rectangles by using limits? And then, of course, if you haven't already mastered the skill, you should be able to draw that squiggly integral symbol without making it look goofy or looking like a treble clef. I think that's what it's called. Noah, isn't that what it's called? Treble clef in music? Yeah, okay, good. See, I'm not as dumb as I look, you know. Okay, here we go. I'll save you the hassle of reading the slide. When we talked about derivatives, we had three things for derivatives. Rate of change, slope of the tangent line, instantaneous velocity. For integrals, the physical representation is the area under the curve. In other words, the area from the curve down to the x-axis. Simple. Okay? And how are we going to work with that? We're going to make a bunch of rectangles to start. Okay? So here's my setup. I've got some curve in red. And that curve is going from 0 out to 10. My starting point will commonly be called A. My ending point will commonly be called B. In this case, A is 0, B is 10. Okay. If my curve, let me rephrase that. If my function were different, let's say it were a straight line, or it was a semicircle, or something that you could geometrically work with easily, then we wouldn't have to go through this hassle. But since it's some weird looking parabola or something, I can't easily find the area under the curve. So I'm going to estimate the area, and that's important to remember. These are estimates, by making a bunch of rectangles. You'll see that the reason this is an estimate is you'll notice all that white area below the curve but above the rectangles. For those of you that don't understand what I'm talking about these regions right here. Okay, that's wasted space, and that's why this answer will be an estimate of the area. Okay? So, again, the concept should be easy. I'm going to approximate the area under the curve by calculating the area of each one of those 5 rectangles. And to start with, I'm going to make my life easy. I'm going to make all the rectangles the same width. Okay? So, 5 rectangles going from 0 to 10 makes each rectangle how wide?
2 units.
Good. Okay? Can we generalize that? Well, if I take my ending point and my starting point and subtract it, I get the distance that I'm talking about. If I then divide by the number of rectangles, I get the width of each rectangle. By the way, excuse me, that distance between, or the width of each rectangle, we're going to refer to as delta x, the change in x. B minus A over n. B is the ending point, A is the starting point, n is the number of rectangles. Okay, things are getting serious here, kids. Watch out. All right, here we go. Are we good so far? Okay, just for giggles, let's take this rectangle. How tall is that rectangle? Approximately.
5.5 units?
Yeah, something like that, somewhere around 5. Let's suppose I told you what f of x is. You could find the height of that rectangle, because notice that this point right here that we measured the height of is actually the y value of the function. So if we knew the function, we could plug and chug. Okay, and we're going to do that later. So that's pretty much the entire lesson. Now, you know it's not going to be that easy. We're going to make things a little bit more interesting by looking at 4 different scenarios. Okay. As I mentioned, we want to find the area of these rectangles, and there's 5 of them. Now, these are called left-hand rectangles. The reason they're called left-handed rectangles is because they're drawn by going up the left-hand side of the rectangle. Once you hit the function, you come across. Okay, so to get this first rectangle, starting at 0, go up to the function. Wherever you hit the function, you come across, and that generates your rectangle. Rectangle number 2, come up the left-hand side, hit the function, come across. And rinse and repeat. Okay. That's the first of our 4 types. Number 1 are left-hand rectangles. By the way, I don't necessarily like this. There's a lot of wasted space. How could I get my answer more accurate?
Maybe use the right-hand side?
One possibility, yes. Other ideas?
I was gonna say, can't we draw the rectangles like laying sideways and then just pile them up on top of each other, or is that not an option?
Ooh. Huh.
We just put, oh, sorry.
Hold on. Yeah, let me finish with that. That is an option, but that's a path we don't want to go down right now because your head will explode. But it would work. We're actually going to do that later on. Okay, somebody else was talking.
I was gonna say, couldn't you just put like the triangles in the space?
Ooh. Ooh. So you want to cheat and do this. Do some more geometry. Something like that? Is that what you're talking about, Rachel?
Yeah, maybe.
Okay. So was it really, or are you just saying that to make me happy?
No, that's what I was talking about. I just don't know if it's right.
Okay, so Rachel, let me ask you a question. If I take this rectangle and I add that triangle onto it, what kind of geometric figure is this? Who'd you have for geometry, Rachel?
Was that last year or freshman year?
That was freshman year. Who'd you have? Was it Kanupke?
This is Helene.
Helene. For geometry? No.
Oh, then I took geometry in middle school. I don't know.
Oh, so your middle school teacher had no idea what they were doing.
Okay.
Do you know the answer? What shape is that? The thing in red.
A 4-sided figure.
Good. What kind of 4-sided figure? Anybody?
Is it a trapezoid?
It is a trapezoid, correct. So, Rachel, you're way ahead of the curve here. We're going to come back to trapezoids, but not now. Okay, we want to stay with rectangles. But yes, you are correct. That would make it a much more accurate answer if we included the triangles in the calculation. Other ideas?
You can make it
Could you use
direct.
line or rect?
Both people talked at the same time and I almost died. What?
Jack, you can go.
Alright, I think I was going to say the same thing. I was going to say you could use finer rectangles.
Good.
Like smaller rectangles.
Perfect. We make the rectangles smaller. So and there's another answer that does the same thing, just answering it differently. We could make the rectangles skinnier, or we could increase the number of rectangles. It's the same results. Okay, because if we go back to this equation, b minus a over n, if we increase n, then the width of them gets smaller, so it's the same results. Good. And in fact, what we're eventually going to talk about is let's increase the number of rectangles to infinity. Oh, that sounds like a limit. And when we increase that to infinity, we'll get a really accurate answer. But that's further down the road. Okay, so left-hand rectangles. Come up the left-hand side of the rectangle, hit the curve, come across. Okay? If there's left-handed rectangles, then you can probably assume that there are right-hand rectangles. Oh, look, right-hand rectangles. Now notice wasted space, but now the wasted space is above the curve. In this guy, the wasted space is below the curve. So Rachel's idea of trapezoids works perfect here. Probably not so good here. But we'll deal with that later. Okay? Right-hand rectangles. And I'll show you what this looks like from start to finish in a minute when we get to the example. I just want to make sure you understand the terminology first. We're okay? Beautiful.
I have a question.
Certainly.
Would you be able to use the integral of the line to find the area under the graph?
That's exactly what we're going to do eventually.
Okay.
But that's a ways down the road. Okay, and yesterday in the not yesterday, when did I see you last? Monday, during the lesson, we talked about that integral being an indefinite integral because when you take the integral, you get another equation. Later on, we're going to take integrals and get actual numerical values, and that numerical value is going to represent the area under the curve. Okay? But again, just for now, we're doing rectangles. So notice my notation. I skipped it over in the last one, but each one of these statements represents the area of one of the rectangles. So notice f of 2 is the height of the first rectangle because it happens at 2. Remember, the y value is I forget, you can't see that. This is f of 2. Okay, the y value of the function, assuming we knew the function. This is f of 4. And then to find the area of a rectangle, you multiply it by 2. So each of these is multiplied by 2. I just factored out the 2 in front. Okay, so let's look at an example here. I've got this parabola, 1/2 x squared plus 2. I'd like to use 3 rectangles to approximate, okay, that's another important thing here, approximate the area under the curve. So we'll do the left-hand rectangles in red, and then I'll change colors and come back to the right-hand rectangles. Okay, how wide are the rectangles going to be?
Two?
Nope. It's a good guess, though.
1.
Why?
Because like the interval is 1 through 4, so there's like 3 like units, and then you can use 3 rectangles, so it will match up well.
Okay. B minus A divided by N. And I'll tell you that most of the time you're going to get a nice value here. It's going to be 2 units wide. It's going to be 4 units wide. You know, something that you can work with. You're not going to get a lot of problems that have a rectangle 1/3 unit wide. That's just silly. Okay, I find these problems easiest to do if you draw an accurate picture. So I'm going to spend a lot of time with this graph, drawing the picture, and then once I get the picture, the geometry is cakewalk. Okay, I'm going from 1 to 4. So here's 1, here's my first one, and I'm going to go out to 4, and each one of these represents a rectangle. So here's how I start the problem. Regardless of whether it's left or right rectangles, I draw some vertical segments up to the function. Okay? And I'm doing the left-hand rectangles first. So this is my first rectangle. I'll label it I. This is II. This is III. So if I do rectangle 1, I come up, since it's a left-hand rectangle, I come up the left-hand side, come across. Whoops, come across. There's my rectangle. Second rectangle, come up the left-hand side, hit the function, come across. Here's my second rectangle. And third time, come up the left-hand side, hit the function, come across. And you can see there's a ton of wasted space here. But that's okay, because we're just approximating. All right, the area of rectangle 1, I know it's 1 unit wide. How tall is that first rectangle?
Units.
I don't know what it is. How would I figure it out?
Plug in 1 in the
Right.
function.
So it would be f of 1. f of 1 is 2.5 times 1 is 2.5. Okay? Don't approximate off the graph. Don't assume that the graph is drawn accurately. Get it off of the function itself. The area of rectangle 2, still 1 unit wide. The height of this second rectangle is f of 2. F of 2 is 4. So 4 times 1 is 4. And then last but not least, the area of rectangle 3, still 1 unit wide. And we're going to do f of 3, which is 9 halves is 6.5. Add 10.5, 12.5, 13 units. Let me stop for a check there. Everybody good on that? No problems there? Beautiful. Okay, now we get into a term called an underestimate. Why won't it write a U there? Underestimate or an overestimate. Okay, so I found the area of those rectangles to be 13. The actual area under the curve is going to be from the curve downward. Is this 13 an overestimate or an underestimate?
Underestimate.
Good. Are we all good with that? There's wasted space below, therefore that's smaller than the actual answer. Beautiful. Questions so far? Awesome. Let's change colors. I'm going to erase this. Are we good erasing here? Yeah. Okay. Clear this out. Oh, I didn't want to erase that, but too late. I'm going to leave those 2 dots there. Can you see those 2 dots? Just because it's going to drive somebody crazy. Okay. All right, right-hand rectangles. I'm going to leave this here and work over it just so you can see the difference between the two. Vertical segments, up to the function. Now we're doing a right-hand rectangle, so come up the right-hand side, come over. Rectangle number 1. Come up the right-hand side, come over. Rectangle number 2. Come all the way up here. Rectangle number 3. Okay. Before I even do the calculations, overestimate or underestimate?
Overestimate.
Overestimate, good. Okay, so rectangle number 1 here still has a width of 1 times, how did I get the height of this first rectangle? It's that, which is f of 2, which we did already, right? 2 squared 4, 2 is 4. Area of rectangle number 2, we also did already. F of 3, which was 6.5. Now a new one. Rectangle number 3 is 1 times f of 4, which is 16, 8, 10. 20.5. Problems, questions, concerns, anything for the good of the cause? Easy peasy lemon squeezy, yes?
Mr. D, I have a question. Is it always gonna, like the problem, is it always gonna tell us how many rectangles we have to do?
First of all, I don't like to use the word always, but I understand what you're asking. And no, sometimes it will say, it'll just tell you how wide to make the rectangles. So that, you know, there's 2 ways to approach this. Start here, end here, use X number of rectangles, how wide is each one? What I could also ask is start here, they're each this wide, how many rectangles do you have? Does that make sense? So they're interchangeable. Okay.
Okay.
Good.
Thank you.
Yep. Anything else before we move on? 2 of 4. We're halfway there. By the way, I did this already. Wait, did we get 13? Yeah, okay, good. And what did we just get, 20.5?
Yeah.
Yeah, beautiful. Those pictures look neater than the pictures I had, but I forgot I had done this already. Okay. Let's change it up. Left-hand rectangle, left-hand and right-hand rectangles always follow that scheme. Go from the left-hand side of the rectangle, go from the right-hand side of the rectangle. Upper and lower sums change the rules. Upper rectangle says your function is always above the curve, always an overestimate. Lower sums, always below. Okay, so here's some examples of the two. The middle picture in pink is what we eventually want to work towards. That's the exact area under the curve. And we'll use an integral to get that later. To the left of that is what's called a lower sum. Every one of those rectangles is below the curve. But if you look carefully at them, some of them are left-hand rectangles, some of them are right-hand rectangles. Okay, so we don't care about left and right when we're doing lower sums. We just want to make sure they're always below the curve. All the way to the right are upper sum rectangles, also known as circumscribed, by the way, in case you didn't see that. Inscribed for lower sums, circumscribed for upper sums. Regardless of whether the rectangle is left or right, it must always be above the curve. Left-hand and right-hand rectangles will sometimes be overestimates, sometimes be underestimates, depending on the shape of the curve. That changes for upper and lower sums. Lower sums are always underestimates. No exceptions. Upper sums are always overestimates. That's summarized in that statement right there. Okay, the middle part is the actual area of the region. The upper sums, this guy is always greater than. Lower sums are always less than. Okay? So the process that I went through to find the left-hand and right-hand rectangles is a little bit different than what I'm going to use for upper and lower sums. It just requires one different step. Can I move on from this? Are you good? Okay. Here we go. Okay, so we're back to this same example. Exact same problem, I'm just choosing to do it differently, upper sums and lower sums, or inscribed and circumscribed. So let me set it up for you. I'm just going to draw the picture, and we'll go from there. So notice I have a different delta x here. Delta x is equal to 4 minus 0 over how many rectangles? 4 rectangles. Oh, look, it turns out to be a pretty answer of 1, keeping it simple. Okay, so start with my vertical lines, or segments, I guess they should be. 0 to 4. And with upper and lower sums, I have to decide, am I going to go from the left or am I going to go from the right to keep it below the curve? So, for instance, if I'm doing inscribed first, which is lower sums, if I look at this first region, I have to go from the left-hand side in order to keep that rectangle below the curve. And what we're going to realize in this example is that left-hand rectangles and lower sums are the same in this problem. Now, why is that? Well, we'll get to it later, but I will give you a hint that we're going to talk about the shape of the curve. Is the curve increasing? Is the curve concave up? Is the curve decreasing? Is it concave down? When we look at those 4 things, we'll be able to talk more about the rectangles. For now, I just want you to understand the process. If I was doing circumscribed, I would have to guarantee that that the rectangles stay above the curves. And so we'd have something that looks like that. Okay? Then you go do some geometry. We're done. It's just rectangles. Okay? Questions about that? Take the time and make your life easy by doing a careful graph. If you do a careful graph, then it'll make your life a lot easier because it becomes a visual problem. How do I figure out, for instance, the height of this particular blue rectangle? Well, I realize that that's the key point that I need right there. That's the height of the rectangle. What is that? That's f of 3. Okay, you can go do the rest of that stuff. Now, how are you going to do that? I believe you can, well, I don't know. Can you cut and paste out of Desmos? Can you do a graph on Desmos and then paste it into Notability?
You could screenshot it. And
Oh,
then just,
there you go. Okay. So you could conceivably go to Desmos, graph it, screenshot it, and then paste that, and then you can draw a careful graph. Or if you're good with graph, whatever you want to do, I don't care.
So you like solved these the same way as you solved the other ones?
Yep.
It's just different in the setup?
Right. And I'm going to end by reviewing those 4 things. Okay. Left-hand rectangles always go up the left-hand side of the rectangle, regardless of the shape of the curve. Right-hand rectangles always go up the right-hand side of the rectangle, regardless of the shape of the curve. Upper sums, also known as inscribed, must always be below the curve, like this puppy. Upper sums, also known as circumscribed, must always be above the curve, like the right-hand side there. Okay. And again, we'll talk later about, well, does the curve go up and is it concave up, or does it go up and it's concave down, etc., etc., etc. For now, I just want you to get comfortable with the idea of drawing some rectangles, finding some areas. And remember, these are approximate areas. The things that we talked about early on with how to eliminate the wasted space will come into play later on. Okay, we'll start talking about limits and that kind of stuff.